Electric charges outside the surface will not contribute to the electric flux. There are three possibilities for a zero electric flux. One very obvious one is that if there is no charge enclosed, then that implies that Q enclosed is equal to 0, which then tells you that the electric flux through the Gaussian is 0. Of course, not a surprise. The second one is that we have no net enclosed charge. Again, implies that I could have an enclosed charge where I have two different charges, where I have maybe charge A minus charge B, but they have equal magnitudes. And that would then give you 0. In this case, we would then have that the flux is then going to be where the flux coming in plus the flux going out, that combination would be 0. So what's a possibility here? Suppose we have an electric dipole. So let's draw the electric dipole. So I'm going to say that here's my positive charge. Here's my negative charge. And I think I'll leave it there. And so this is positive, this is negative. So now let's start looking at the field lines. So the charge goes from here to here. Excuse me, not the charge, but the field. And then the field is fringing like this. And then let's say that we have another larger loops, trying to draw them symmetric. And then of course there's going to be a charge, not a charge, I keep saying charge, but a field that's looking something like that. So let's say this is my dipole field. Now, because of this, what I want to do is that I want to copy this and put it over here. So now what I want to do, so I have an electric dipole. Now draw a Gaussian enclosing both charges. And look at the flux. Now I'm going to say that I want to lower this down. Really, the one on the right is the one that's more important. And so if I do that, so now here's what I'm going to do. So now I'm going to draw a Gaussian. So as I draw the Gaussian, what I need to do here is that I want some of them are going to get covered up. And so if let's say that I choose my Gaussian right here. So what am I seeing with this Gaussian here? Now, a Gaussian is supposed to be opaque because we want to know what's on the inside. So what am I going to do? I'm going to start coloring this. So I don't need to know what's inside. What I need to know is where are the field lines of the Gaussian. Now I can keep drawing over this and just hide all the lines, but let's go look at that. So again, if I'm talking about a Gaussian, what I'm saying is that right here, we're talking about that we can't see inside, but we can count field lines. So let's look at the top line. So if I look at the top line, note that I have a field that came out, and let's call this field line 1. And clearly here, you're seeing here that it's going out, and then right here, it's going back in. And then I could go in and I could look at the next one. If I look at this one here, I could see that this field line is going out and this field line is coming back. So let's call this one 2. So again, this one's going out, this one's coming in. And then finally, I have another field line. And I'm looking at this guy. And you're seeing here is that that's coming out and this one's coming in. And I'll call this 3. So this is out and this is in here. So what I want to focus on is that if I look at the flux here, what do I actually see from the flux? Well, if I look at the total flux, okay, so now I'm going to look at the net flux. I should see that it should be the flux due to the, let's not call it purple, how about violet, plus the flux of the red, plus the flux of the orange. Oops, did not spell that right. And so if I look at the violet one, we clearly see that we have one coming in and one going out and one coming in. And if I look at the red, I clearly see one is going out and one is coming in. And then finally, when I look at the orange one, I have the exact same thing. So if I start to count these flux lines, you're going to see here that clearly I have 0 field lines poking through the surface. So in other words, that tells me that the net flux is 0, also implies that Q enclosed is 0. But we knew that already because it was the dipole. Okay, so that's a second possibility. Now we go to the third one, which is, in my opinion, has a lot of misconceptions. So now we're going to have outside charges do not contribute to the net flux of a Gaussian. So now what we want to do is that we want to suppose that we have a Gaussian that contains a collection of charges. Okay, so suppose a Gaussian, and in this case, you're going to see that I'm going to choose a cubic shell. Contains one red positive charge, while there are two external charges. And these charges, I'm going to call them green and blue. So picture-wise, I imagine something like this. I'm going to take my my cubic shell, and the way I'm going to arrange them here is that this charge is purposely off-centered, and then I have a green charge over here, and then I have a blue charge somewhere right there. So I'm going to make this green charge negative, and then this is positive. So when I look at this, very similar to what we did before, what does Gauss's law says? So Gauss's law states that the net flux should be the flux of the red plus the flux of the green plus the flux of the blue. And this should be proportional to the enclosed charge. Well, let's look at each of these situations here. So the first thing that we want to focus on is that let's look at the green charges. So now we want to look at the flux from the green charge. And what we're seeing here is that if I paste this back in, like right here, what I'm seeing here is that I'm going to look at the field line. So now, if I look at this field line, let's say it goes like this, and then you could see here, it then comes out here, and I can do this again. And I'm only looking at the flux here at the surface of the Gaussian. So when I'm looking at the green here, you can see here is that these guys, and this is the crazy part, look at what's in. Right in here, this is where it goes in. Right? It's going in, and out here, it's going out. And you might say that's quite strange. Remember, the field lines start at the negative charge and go outwards. So now when you're looking at this, you could see that in each situation, I could then say that the flux of the green is equal to what's coming in. In this case, what's coming in here is going to be, let's say, the flux coming in plus the flux going out. Well, that's going to be zero. In other words, we're seeing, let me bring this down here. What this implies here is that there's no net field lines for this situation, right? Is that a good way to say it? There's no field lines. The flux is always zero. There's none that are poking through, right? There's no net field lines poking through the Gaussian. So this implies then that then the enclosed charge of the green in that Gaussian, of course, is zero. So the green charge does not affect the flux through that. Now I can repeat this process for the blue, right? And again, in this statement right here, we could say that, of course, we already knew this. I'm just being complete here. Now, look what I could do next here. Now I look at the blue charge. Now the blue charge is very similar to the green charge. So now, if we repeat the same process for the blue charge, we conclude that the flux of the blue is going to do the exact same thing. I'm going to have a flux coming in. I'm going to have a flux going out. And of course, that's zero, which then says that in the Gaussian, there is no blue charges there. What a surprise. We knew that already. So now the last thing I want to say here is that now we want to repeat this for the red charge. So if I ignore the green and the blue because we already dealt with them, we can see here is that I'm going to have a higher field there. This guy is probably going to be the exact same magnitude because it's the same distance. This one should be smaller, and this one should be a little bit bigger, but that's the flux. So when I count the field lines, we could then say that the flux of the red equals 4 lines going outwards. Therefore, we conclude then that the enclosed charge of the red must be plus 1e. So if I summarize the whole thing here, so in summary, Gauss's law says that if I have a net flux, then this would be the flux of the red plus the flux of the green plus the flux of the blue. But in each of these situations, the flux does not depend on those at all because they're external. This is only the flux due to the red charge, and therefore this should be the enclosed charge is then going to be for the red plus the enclosed charge for the green plus the enclosed charge for the blue. But when we look in here, we can immediately conclude that, of course, there's no green there. Of course, there's no blue there. And so we then find that it's the flux. So this tells us then is that the only flux we can measure is the one produced by the enclosed red charge. The blue and the green will not contribute to the flux. So charges external to a Gaussian will not contribute to the flux of the enclosed charges. So just to make it a little bit more tighter here, because I want to box this guy, this is the main point of what I just covered right here. The key point being what? Key point. The only thing that matters in calculating electric fields using Gauss's law is the enclosed charge, not anything else. Now, this leads to a really, really great question that really has lots of misconceptions. It's very, very, very easy to have these misconceptions. So what we want to do here is that we want to ask the question about inner and outer electrons. So really, here's the main question that I want to answer. Do outer electrons affect inner electrons in atoms? And I think that's a really, really great question. And it leads to a lot of misconceptions of what's going on. So here's what we know. We know that inner electrons use charge screening for outer electrons that reduce the effective nuclear electric field that they feel. So, rephrasing the main question, do outer electrons affect the inner electrons? So, if the inner ones affect the outer ones, do the outer ones affect the inner ones? So, the question that I'm asking, does this mean that outer electrons push inwards on the inner electrons, forcing them closer towards the positive nucleus. So I'm going to deal with a more complicated atom, and I want to deal with copper just because we've dealt with copper in the past when we're dealing with atoms. So let's focus on this. So suppose we look at copper atoms and focus on the 29th electron in the fourth shell. So if I look at my picture of the copper atom, what I'm seeing here is that I really have a positive nucleus. And of course, we know that the positive nucleus here has 29 positive charges due to the proton. So now if I look at these shells, I have 1, 2, 3, 4. And this is what I know. I know that this guy has 2, this guy has 8, this one has 18. In other words, if I start counting these electrons, I have 2, 8, 18. So when I look at that 29th electron, it is all by itself on the fourth shell. Now, one of the things that I have to worry about is that quantum mechanics plays a huge role. So this is what I want to do. You could imagine that I use Gauss's law. So let's look at Gauss's law. So you could imagine then, since I have a spherically symmetric charge, I could put my Gaussian right in here. And as a consequence, we then have the following thing. So I'm putting my Gaussian on that encloses, right? So the Gaussian, I should say, encloses the first 3 shells plus the nucleus. So from Gauss's law, the 29th electron will not contribute to the electric flux. Note that I did not say electric field. Will not contribute to the electric flux inside, not inside, the electric flux of the Gaussian. Because this charge is outside the Gaussian. Right? And this is what we just showed right here. This is exactly what we were talking about. The green and the blue are not going to contribute. So when I look at this copper atom, the 29th is outside and will not contribute. However, it does not mean that the 29th electron doesn't apply an electric force on the inner electrons. And the ones we really got to think about, we really are talking about especially the third shell electrons. Those are the ones that are closest. So then the question then lies like this. Wouldn't this 29th electron affect the E field of the inner shell electrons? We're talking about 1, 2, and the third shell. And in essence, this dilemma seems to violate Gauss's law, right? It seems to violate Gauss's law. And the thing that we're mistaken here is that we're confusing flux with electric field. It is a misconception to think that just because the 29th electron is outside the Gaussian, that it will not have an effect on the electric field inside. I know I did, so I'm imagining that you might too. And part of the reason is that I was mixing up flux with the electric field. So, in other words, the total flux of the 29th, oops, is indeed 0, but that doesn't mean there is no influence. So the misconception is that people mix up flux with the electric field. So let me give you an example here. So imagine that I have a charge, a point charge, and I'm going to draw it up to a Gaussian. So as we were talking about, you could imagine that here's my 29th electron, and then I'm going to draw my Gaussian right here. So when I look at that Gaussian, remember, we don't care about what's inside. So now let's follow the field. So when I look at the field, note that it comes in and then it goes through and then it goes out. So what you're seeing here is that clearly something goes in, something goes out. So when I look at this thing, the flux of the green here is equal to the flux of it coming in plus the flux of it coming out. And since they're equal numbers and they're opposite, that is clearly 0. However, there is still that red field line inside the Gaussian. And because it's still there, that implies that outer electrons apply an electric force on inner electrons. Even though the flux is 0, we're seeing here is that the flux external affects the internal E field. which is crazy. So once again, so when I look right in here, I can see here is that the electric field inside is not zero. Now, this is probably a little bit too advanced, but I think it's interesting that we should just talk about it because we're here. And we will address this at the end of this chapter. Now, the situation for copper, before I move on, note that there's a lot of quantum mechanics in here. And because there's a lot of quantum mechanics, I mean, I'm missing a lot of the pieces here. So just note that this is an incomplete picture still. The situation for copper is slightly more complicated because the electron in the fourth shell is in a spherically symmetric orbital. This does reduce its influence on the inner electrons, but not because of Gauss's law. But, no, not but. The issue here is the third shell is a full shell and effectively acts like a conducting shell. And this is something that we're going to look at the end, in the next couple of lectures. So if I have an electric shell like this, that no matter what, we're going to find is that this is a conducting shell, we're going to find that inside of here, it is exactly zero. So the field vanishes inside of it. So if I apply this to a copper atom, so applying this to a copper atom, here's what we find. So if I look at this, I have a nuclear charge right here. Right, here's my nuclear charge. And so now I have shells. If I have full shells of electrons, when I look at that third shell right here, that third shell has 18 electrons here. So if I look at this third shell right here, this has the third shell in copper has a full 18 electrons. And these guys act like a conducting shell. So now, if I look at the electron is in a spherically symmetric state as it's going around here. And what I'm saying is that this here is the fourth shell. But when I look at this, I'm seeing that I have charges that are spherically symmetric in this shell, and they act like a conducting shell. So then that means that the influence of this electron right here is going to be less, not because of Gauss's law, it's because of the conducting shell. This is a super complicated topic and a super interesting one. Hope you enjoyed it.